Okay, this is the video walkthrough for the in-class assessment completed in April 2021. It's a chance for you to go through, have a look at the work that you completed on your paper, compare it to the answers on here, and there's also hopefully a little bit of opportunity to look at developing your understanding with some additional information as we're going through. So I'm going to jump straight on. We're going to get to one A, B and C that we can see here. That's the whole of question 1. And we've got a number of elements that have been included on a nearly blank periodic table. And you've then got to identify ones that fit into a particular category. So let's take a look at 1A to begin. You'll notice that the question asks for metals, so we can have a look at where the dividing line is on the periodic table. I've added that on in green. We know that the answers are going to come from the left-hand side. Now, the purpose of showing you this is that we can then definitely disregard 3 of them, and immediately our odds are improved. We also want to know which ones will react vigorously with water. So that takes us to our knowledge of group 1 metals. One of the big things that we know about group 1 metals is that they do react vigorously with water. Potassium will actually spontaneously ignite with a lilac flame in contact with water. So I combine that information. I know they're metals, so I've narrowed it down. I know that it's going to be group 1 based on my wider knowledge, so that takes me to the answers lithium and potassium. So then we move on to B, the 2 elements with 5 electrons in their outer shell. So the 5 electrons is key here, and this is relying on you having a knowledge of group number and its link to electrons in the outer shell. So group 1 has 1 electron in its outer shell, and group 5 has 5 electrons in its outer shell. I find group 5 on the periodic table, and I can then see I've got my 2 answers to slot straight in. I've got my nitrogen and arsenic. But it is important to point out here that you've got to be really careful with how you write down element symbols, because the second letter of any element symbol will always be lowercase. If you did a capital S on there, it might make it slightly trickier to credit you with the mark. And that takes us finally to part C. Iron has ions with different charges. The other metal that has ions with different charges, well, there's a particular area of the periodic table that do have variable charges on their ions, and that is the transition metals. So I have a look in there. I can see that I've got 2 options. The one that's left is copper. Iron is already there. Now, you don't want to fall at the final hurdle and write down iron because it's in there and not have paid close attention to the question where that's already been provided as an answer. Okay, moving on to question 2. And we've got a method here. We've got hopefully a practical that you're very familiar with. It's one that you will have done in Key Stage 3, and then we revisit it at GCSE. We've got rock salt, which is salt and sand mixed together. We're going to put it into water. That is going to dissolve the salt. The sand won't dissolve. We're then going to get rid of the sand, and then we're going to evaporate to get the salt from the water. Now, if we take a look through, you'll notice I've just gone through the method and I haven't looked at any of the questions yet. When you're given this amount of information in a question, I'd really strongly recommend you take the time to go through every part of it, because then you can very easily refer back to the relevant parts when you're answering the questions. So let's take a look at the questions here. We've got A, B and C. One improvement to step 2 to make sure that all the salt is dissolved in the water. Now, one option is that you could stir it. Whenever you're dissolving things, you will know this in wider life, in real life, away from chemistry, that if you want to put sugar in your tea, if you want it to dissolve, you stir it because it will go faster. The other option is that you could heat the water. You could do it at a higher temperature. And that links to your knowledge of rates of reaction as well, but it would certainly speed up the rate of dissolving. What many people will put down on here is that you could add more water. The problem is that that has an impact later on in the practical. And as a general rule, you would always dissolve in the minimum amount of water possible. So for that reason, you would not be expected to say use 200 cm cubed or use more water. That wouldn't be an acceptable answer. Okay, the salty water in step 4 still had very small grains of sand. What could be done to this method to improve it? So what we're looking at here is how we remove a solid impurity. And again, we're going back to separation techniques that you've probably been familiar with for around 5 years. You're going to filter it. The sand will stay in the filter paper and the salty water will go through into the beaker. And then we want one safety precaution that students could take in step 5. So we're dealing with flames here, and key to any practical, if you think about absolutely everything that you do in the lab, you're generally going to wear safety goggles, safety specs, eye protection. And you are also going to wear a lab coat, you're going to wear an apron, you're going to wear protective clothing. And they are the most important ones. Now, I know that within school we talk about a number of other rules about not moving around, not running around, not tying back your hair. But generally speaking, when you get to an exam environment, they are not what would be considered valid. I would always revert back to safety goggles and protective clothing when it comes to a question like this. Okay, we're going to move on to part D. We've got a diagram here which is showing a different method. And we've got the salty water, and we can see here that we've got a round bottom flask. We haven't got where the letter B is labelled. They've not told you that because it actually guides you towards the answer, and they're hoping to avoid it. Now, the technique works by describe how the technique works by referring to the processes at A and B. Just as a general exam tip, if they are talking about specific letters in specific locations, build your answers around them. So I have highlighted my A and my B here, and then I'm simply going to put A and B down in the space. I'm not going to write a huge sentence. I'm not going to write a paragraph. I'm simply now going to say what the process is. At A, we're heating the water. The water is going to evaporate, so it's evaporation. And then in B, when you have the jacket of cold water cooling that vapour down and you are condensing it to become a liquid again, that's condensation. Now, the final part of here, what's the reading on the thermometer during this process? What we're looking at here is that we have got water evaporating. Water will boil, it will rise up at 100 degrees C. So that's the temperature that we would expect. As I say, just because we know it's water that's evaporating, it's a very common question actually. It's something that comes up a lot. Moving on, we have got a question about the halogens, or group 7. How do the boiling points change down the group from fluorine to iodine? Now, I'm not going to draw all 4 of them, but I have added fluorine and chlorine, not to scale, but showing that as you go down the group, the molecules get bigger. Now, bear in mind you're not having to explain this for the answer, but you do need to understand these principles. Because they're getting, or one of the reasons they're getting bigger is that they have got more electrons. You're adding electron shells. And because you've got more electrons, you have got stronger intermolecular forces. And if the intermolecular forces are stronger, more energy is needed to overcome them. So we know that the boiling points will increase as you go down group 7. Moving on, we've got sodium bromide produced by reacting sodium with bromine. Sodium bromide is ionic. Write down the symbols of the 2 ions. So the first thing is to pay attention to the question. There are 2 of them, and we know that sodium is Na, and we know that bromine is Br. So we know that they are going to be the component elements. But these are ions, and that means they need charge. Now, sodium is in group 1, and it is expected that you will remember that group 1 atoms form ions with a +1 charge. And similarly, group 7 elements that need to gain 1 electron to get a full outer shell will form ions with a -1 charge. So you need to have those charges in there to be credited. Moving on to part 2, where we have essentially got a displacement reaction. The chlorine in this place displaces the bromide. So we have then got to consider what the other product will be. Well, if the chlorine is kicking the bromide out, that's now going to be what's combined with the sodium. So we have got sodium chloride as the other product. The big consideration to make here is that when halogens become ions, we change the N to a D. So chlorine forms a chloride ion, bromine forms a bromide ion, fluorine would form a fluoride ion, iodine, iodide, etc. Okay, let's move on to part 3 of this question. Why does chlorine displace bromine from sodium bromide? Now, to give a little bit of background here, we're linking it to our knowledge of displacement reactions generally, that are more reactive can kick out a less reactive. We often refer to that with metals, but we do need to know it for the halogens as well. So the simple answer here is that it's more reactive. And then we're going to use the chemistry data sheet, that's the periodic table, to answer this question. Which halogen could react with sodium chloride solution to produce chlorine? So we're asking here, which halogen is more reactive than chlorine? And we know that reactivity decreases as you descend group 7, or we certainly need to know that fact. Now that means that if I put them in, and I've added my fluorine, chlorine, bromine, iodine here, reactivity increases up the group, so the only halogen that could actually displace chlorine is fluorine. We move on and we take a look at another practical. We've got here an investigation of the law of conservation of mass. The mass of product is equal to the mass of reactants. Again, I really recommend you take the time to read through the whole method before you answer the question. We're going to pour lead nitrate into a solution into a beaker labelled A, potassium chromate into a beaker labelled B. We're going to measure the mass of both beakers and contents, pour the solution from B into A, measure them again, and then from there we're hopefully going to prove that the law of conservation of mass is taking place. When lead nitrate solution and potassium chromate solution are mixed, a reaction takes place, and we've got an equation provided. Now the first question here, what would you see? You'd want to avoid trying to guess what might happen here. We want it to be based on the information that's provided. For example, you might talk about there being colour changes. Some people might write down effervescence. There's actually no evidence here that this would effervesce. And we can touch on that by getting to the final answer. We need to look at the state symbols. They are absolutely key to what we need here. And you'll notice I've highlighted these 3 as aqueous. I've taken an aqueous solution and reacted it with an aqueous solution. I have, in part, with one product, made a new aqueous solution. But I've also made lead chromate, and that's solid. So if there wasn't a solid before, we are going to see a solid formed. You might well say here precipitation. You could arguably talk about crystallization because it is an ionic compound and we would see crystals forming. But we need this answer to relate to the idea that there is a solid formed. Then we move on to part B. We've got a table of results. Show that the law of conservation of mass is true. Use the data. So what we need to look at here is A and B before and after the reaction. And if I add those up, and I've colour coded so you can see the numbers, 128.71 plus 128.97 gives 257.68 grams. And if I do the same with the 2 yellow numbers from A and B after mixing, they also come to 257.68 grams. Now this has shown us that the mass hasn't changed. But we are being asked to say how this shows us the law of conservation is true. The numbers aren't explanation enough. So we need to say that overall the mass is the same. It's unchanged after the reaction compared to what we saw before the reaction. We move on to part C, and I've brought the table forward again so we can have a look very, very carefully, because we want to know what resolution the balance had. And we can see that in every single case here, the mass that we measured had 2 decimal places. Now that means that the balance must go to at least 2 decimal places. And that means that the answer is to 0.01. That is the smallest value that could have been measured based on what we can see in that table. Okay, let's move on to part D, a relative formula mass question. You calculate relative formula mass by adding relative atomic masses. They've been provided here, but if they're not provided to you in the exam, this is the bigger of the 2 numbers on the periodic table. So I've written down here the lead nitrate. I'm now going to start substituting the figures in. I've got 1 Pb, that's 207. I've got 2 nitrogens because the NO3 is in brackets and there are 2 NO3s. And by that same token, I have got 6 oxygens because there are 3 oxygens in 1 NO3 and I have 2 of them. So I put all of those numbers together and I've simply then got to multiply up and then add together, bringing us a relative formula mass of 331. Okay, we're going to move on. The formula of potassium chromate is K2CrO4. This isn't something you'll be familiar with. You are told the charge on a potassium ion is +1. So what's the formula on the chromate ion? Now, you may not have been told that potassium is +1, but you would know it because group 1 ions are always +1. So I've put that information in, and then we can use a seesaw to actually balance them out because the overall charge on my compound is 0. If I've got 2 Ks, that's 2 + 1s. I've got 1 chromate ion, so that must be -2. So I'm going to go for CrO4 -2. We move on, and I have got here another student testing the law of conservation of mass using the same method. And we're going to have to look at the state symbols to answer this question. Because I've started with 2 aqueous solutions. I've made an aqueous solution. That's not going anywhere. I've also made liquid water, so that's going to stay in the container. But this is really important. We've made a gas. So carbon dioxide is a gas. We know that. We know it anyway, but the equation has told us. And we know that if you make a gas, it will, from the effervescence, the gas will escape into the atmosphere. And if the gas escapes, that means that we aren't able to measure the mass of it. So it would appear that the mass has gone down, and the mass would be lower than the law of conservation of mass would suggest it would be. Moving on to question 5, and we have got here actually a very straightforward question, because we're saying we've got 2,000 tonnes of hematite, 70% of it is iron oxide, so how much of that 2,000 tonnes is iron oxide? So I'm going to find 70% of 2,000. I get to 1,400 tonnes. But we then move on to a slightly more complicated calculation. Calculate the amount of iron that can be extracted from 2,000 tonnes of hematite. I have also transferred the equation, which is not yet balanced, onto this page as well. And we're going to need to use that to answer the question. Now, I'd always recommend using a table for reacting masses, and the table always has this format. You have mass, molecular or atomic mass, moles, and mole ratio. I'm then going to transfer in my species that I want to know the mass of and my species I know the mass of. Now be very, very careful because it's 2,000 tonnes of hematite, but we've just established not all of that hematite is iron oxide. But iron oxide is the one I'm interested in. So I know that I had not 2,000, So what we're actually going to do is we are going to amend this, because actually, as we established on the previous section, it's 1400 tonnes. Now I've also added in the molecular and atomic masses. Iron has a mass number of 56, we're told this in the question again. Iron oxide, with 2 ions at 56 each and 3 oxygens at 16 each, has a molecular mass of 160. Now at this point I can use the mole triangle, or the mole equation, to work out the number of moles, mass divided by molecular mass, for iron oxide. And 1400 over 160 will give me 8.75. To get to the other side of the table, I need to use mole ratios. Now this equation here is not balanced, because I've got 2 ions on the left and 1 on the right. So I'm going to balance it, but I'm also then going to use those balancing numbers to put into the mole ratio. 1 mole of iron oxide will give us 2 moles of iron. Now I know that if the ratio is 2 to 1, I can follow that ratio up to the actual number of moles, so I'm going to double the 8.75, and that means I've got 17.5 moles of iron. And again I go back to the mole triangle. Because I've got atomic mass and I've got moles, I can multiply those together, and that takes me to the final answer of 980. Going to move on to part 6. History of the periodic table here. By 1869 there were around 60 elements discovered. Mendeleev put them in a table in order of atomic weight. He put elements with similar properties in the same columns. Now we can see an example of his table from 1869 here. Name one element in group 1 of Mendeleev's table that is not in group 1 of the periodic table on the datasheet, and give a reason why it isn't. So you really do need to be looking at the periodic table provided when you're answering this, just to make sure you are absolutely clear on what you need to do. So have that with you, take it, have it clear and visible as you're answering the question. We're interested in group 1. Now group 1 I have highlighted in blue, and I'm then going to go through and I'm going to highlight the group 1 metals that are in the modern group 1 periodic table: lithium, sodium and potassium. And again, we've learnt about those in terms of their reactivity with water. But that means we've got 2 potential answers here. You could have gone for hydrogen. And why should it not be in group 1? Well, the most obvious answer here is that it's not a metal and all of the others are. But you could also have gone for copper. And copper does not have 1 electron in its outer shell, which is a valid reason for that also not being in group 1. So moving on to the next question here, which group of the periodic table on the datasheet is missing from Mendeleev's table? And it's slightly easy to go wrong on this one, because if you look at the numbers, we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 is commonly known as 0. And so we think, okay, what's missing? That big section in the middle, transition metals. No. What we are interested in is which group elements do not appear. And iron, cobalt and nickel. And actually beyond that, we've got lots of others. We've got zinc, we've got copper, which are all transition metals. So they were present. They just weren't separated out as transition metals. What's missing is the noble gases. And that's because they hadn't been discovered at this stage. And they hadn't been discovered because they're so unreactive. So we wanted group 0, group 8, the noble gases for that one. Continuing with the question, we've got gaps where Mendeleev knew there would be elements that would be discovered that had not yet been discovered. So we're then having a look at period 4 on the periodic table. And this is really important that you're picking from the right place. Again, you need to have your periodic table with you. This is the table that you're provided with in the exam, and this is period 4 going across. Within there, if you actually cross-reference the two, all of them appear in Mendeleev's original table that's being provided, apart from 3. And they are scandium, gallium, and germanium. So you had to pick one of those. Moving on in the question, Mendeleev was able to make predictions about the undiscovered elements. This eventually led to most scientists accepting his table. What predictions was he able to make? Now, bearing in mind that the periodic table is built around similar elements being put together, there are a range of things that you could talk about here. You could talk about the fact that he predicted the chemical properties, the physical properties. You may have even picked out specific chemical or physical properties, like how they react with water, or their melting point, or their boiling point, or their density. You could also have spoken here about the relative atomic mass, that he would have predicted what the atomic weight or the atomic mass would have been. He wouldn't have predicted the atomic number, because at that point we weren't working with atomic number. He'd organised it in terms of atomic weight. Moving on, why are lithium and sodium both in group 1? I've already touched on this going through some of the other questions, but let's look at their electron configurations. Lithium is 2-1, sodium is 2-8-1, and they both have 1 electron in their outer shell. Carrying on, why is sodium more reactive than lithium? Going to give you quite a lot of information here so that you can it's not just to get to the answer, it's to understand why it's the answer. And a good start point here is to draw out lithium and sodium. Lithium with 2-1, sodium with 2-8-1. And then we can play spot the difference to try to work out why sodium would be more reactive. First thing that stands out is that sodium atom is larger than a lithium atom. If it's larger, that means that the outer electron is further away from the nucleus. And if there's a greater distance between the positive ion and the negative ion, it means that there's going to be less attraction. There's also more inner electrons on sodium, and what they will do is shield the outer electron. They'll repel it, they'll push it away, and so they will be repelled more in sodium. And if I've got less attraction to the nucleus and more repulsion by inner electrons, then I'm going to have to provide less energy to sodium to lose an electron than I would have to provide to lithium. So because sodium loses its electron more easily, that means it's more reactive. Okay, moving on to question 7, we've got silicon dioxide here used as a lining for furnaces. We think about furnaces, very high temperatures, that's key in a second. Got a diagram there. And we've also got silicon dioxide provided. And I'm hoping that what you can see here is, although you don't learn explicitly about silicon dioxide, it has a very similar structure to diamond. And this is a question that's asking you to apply your knowledge of diamond. It will work in exactly the same way. So, why is silicon dioxide a suitable material for lining furnaces? Well, taking your knowledge of diamond and applying it to silicon dioxide, it's a covalent compound. But more than that, because there are 2 types of compound that have covalent bonding, molecular covalent and giant covalent. And this is a giant covalent compound. It has lots of strong covalent bonds. And if you want to, or if you were to melt a giant covalent compound, you would need to provide lots of energy to overcome all of those strong covalent bonds. Now, because it's giant covalent, that means it has a high melting point, and that takes us back to this idea of we're making a furnace. We want that furnace to be able to withstand high temperatures. If the wall's melted, that's not going to be so good. Okay, that takes us to the end of the walkthrough. I'm hoping that's provided some guidance. It's given you some recaps on some of the key ideas. I think anything that you're not so sure on when you've gone through this, if there's any content that you're still a little bit rusty on, not quite up to speed, take the time to go back over those topics again. Think about the questions that you need to ask. Go back to your teachers and make sure you ask them prior to the final assessment in a few weeks' time. Okay, best of luck. Thank you for listening. Bye-bye.